You're building a wooden bridge for your physics experiment, okay? And let's say that the maximum capacity of this bridge is 100 kilograms. So it can support up to 100 kilograms, but even a single gram above that, it will not be able to support it, okay? Now, the question is, can it support the weight of these 3 rocks? Well, for that, we just need to figure out the mass of them, right? So we individually measure the mass of each rock. The first one is measured to be this much. The second one is measured to be this much. And the third one is measured to be that much. Now, the question is, will our bridge support the weight of these 3 rocks together, or will the bridge collapse? How do we answer that question? Well, we just have to add up their masses and see if it's more or less than 100 kilograms, right? So let's do that. Let's add them all up. And to do that, we just plug this into our calculator. And when you do, you get the answer to be 99.636 kilograms, which is less than 100. So we confidently claim that because that's less than 100 kilograms, yes, our bridge will be able to support their weight. And when we test it out, we find that the bridge collapses. What? Why did it collapse? And what does it mean? Let's find out. Let's go back to our measurements and look at that a little bit more carefully. Remember that the last digit of a measurement is always an estimate. So in the first measurement, this digit is an estimate. So we don't have any confidence in that. It's possible that this could be 3, making the mass 64.3 kilograms, or it could be slightly more, maybe 5, making the mass 64.5 kilograms. So there is some uncertainty over here, okay? Now in this measurement, this digit is an estimate. So we don't have confidence in this particular digit, which means the mass could be 18.235, for example, or it could be 18.237, slightly more, for example. Can you see that this is a much more precise measurement compared to this one, because the uncertainty is in this digit over here. But what about the last one? Well, look, this is the estimate over here, which means the mass could be, 1 less, let's say. So it could be 16 kilograms, or it could be slightly more, 18 kilograms. This is such a huge uncertainty. So ask yourself this question. Look at all these 3 values added up. Do you really think the answer is going to be exactly 99.636 kilograms? Of course not. The value with the lowest precision that you see over here, that's going to mess things up. You can't just throw in a measurement of 17 kilograms, which has at least an uncertainty of a kilogram, and expect your answer to be precise down to a milligram. That's just not possible. Our summation cannot be any more precise than the least precise measurement. Have you heard of the saying, only as strong as its weakest link? Yeah, the same idea over here. So this answer can only be as precise as the least precise measurement, and that is this one. And that's the mistake that we have done. We haven't precision corrected this measurement. So in the rest of the video, we'll see how to do exactly that. So how exactly do we do precision correction? Well, there are 2 rules. It depends on, whether you are adding and subtracting measurements or whether you're multiplying and dividing measurements. For this particular video, we'll focus on addition and subtraction, and in the next video, we'll focus on multiplying and dividing measurements. So let's consider this one. What we do when we're adding and subtracting measurements. Well, the rule is this. The answer can only have as many digits to the right of the decimal as the value with the fewest digits to the right of the decimal. Don't worry, I know it sounds very complicated when we spell it out, but let's do some examples and it'll make a lot of sense, okay? So consider this particular summation, okay? The first step is we just plug these numbers into our calculator and see what the calculator gives us. And over here, it gives us 32.017 meters, okay? But this is not precision corrected. So how do we do that? Well, we have to first find the value which has the fewest digits to the right of the decimal. So this has 2 digits to the right of the decimal, this has 1, and this has 3. So look, this is the one that has the fewest digits. And how many? It has only one digit to the right of the decimal. This means our final answer should also have just 1 digit to the right of the decimal. In other words, we have to round this off to make sure that it has only 1 digit to the right of the decimal. And that's it. That's how we precision correct. Okay. So now the last thing is just to round this off. I used to get confused while rounding as well. So let's do this slowly and step by step. We have to round this digit because this is where we need to end. And we do that by looking at the next digit. And we can ignore all the other digits around that. So let's forget all of that. Okay. So now let's look at this digit. And if this digit is between 0 and 4, we round down, meaning we keep the same value. And if that digit is between 5 to 9, so it's about 5, then we round up. So it would go to the next number. In our case, this digit is between 0 and 4, so we round down, meaning this digit stays as is, so 0. So our final answer is going to be 32.0 meters. This is how we precision correct it. Okay, so let's go back to our rocks. How would we precision correct this? Well, first we find the value which has the fewest digits to the right of the decimal. This has 1 digit to the right of the decimal. This has 3. This has none. So this is the one that has the fewest. It has 0 digits or no digits to the right of the decimal, which means our answer should also have no digits to the right of the decimal. In other words, we have to round this off to make sure that there are no digits to the right of the decimal. So again, let's do it slowly. We have to round this digit off by looking at this digit, and we can ignore the rest. So again, the rule is the same. If it's between 0 to 4, we round down. If it's above 5, we round up. This is above 5, so we round this up. So this becomes 9 goes to 10, and then 1 carries over, so you get 100. So 99 gets rounded to 100. And because we know that these two zeros are actually significant, we need to mark them. And the way we do that is by putting a decimal point. Now, don't let this distract you. Our rule here for addition and subtraction is actually about digits to the right of the decimal. But we should always report our final answer with the correct amount of significant figures. And now that we have marked these two as significant, we are actually reporting that, look, this last digit, that is our estimate. And so we are reporting that, hey, this could be a little above 100 kilograms, or it could be a little below 100 kilograms. And now we could say that, hey, you know what, when we keep these on the bridge, it's possible that the bridge could collapse. This is how we accurately report the measurement. Makes sense, right? All right, let's try a few more problems. Let's try a subtraction problem this time. And there's no difference. The idea is exactly the same. So feel free to pause the video and try it yourself first. Okay, let's do it. So first step is to plug this into your calculator and see what the calculator gives you. The calculator gives me 116.8 grams. Then find the value which has the least number of, or the fewest digits to the right of the decimal. So this one has no digits to the right of decimal. This one has 1 digit to the right of decimal. So this is the one that has the fewest one. So no digit to the right of decimal, which means our final answer also should be rounded off to have no digit to the right of decimal. In other words, we should round off this digit by looking at this digit. So again, we see whether it's between 0 to 4 or above 5, and we see that this number is above 5, so we round this up to 117, and that is our answer. So the value over here is 117 grams. All right, a few more problems for you to try, so great to pause the video and try them all. Okay, let's do the first one. Again, first step is to plug this into our calculator, and when we do that, we get 104.88 ml. Then find the value which has the fewest number of digits to the right of the decimal. This has 2 and this has none. So look, no digit to the right of the decimal, and therefore our answer should also have no digit to the right of decimal. So this means we need to round this digit off by looking at this digit. So I can get rid of this. And again, the same rule, since this is above 5, we round this up, and so I get 105 ml. That is our final answer. All right, let's look at this one. Again, we plug this in our calculator to get this. Now, let's look at the digits to the right of the decimal. No digits to the right of decimal, no digits to the right of decimal, 1 digit to the right of decimal. So these two represent the fewest, you can take any one of them, but these two represent the one which is the least precision. So no digit to the right of decimal, which means our answer should also have no digit to the right of the decimal, which means I should round off this digit by looking at this digit. And when I do that, since this is 0, so I just keep the same number. I round down. And so the digit stays put, and that's our answer. So that's our final answer over here, precision corrected. All right, one last. Let's do this. Plug in our calculator, plug into our calculator. This is the number we get. Now let's look at, there are so many decimals. Okay, this has 3 digits to the right of decimal. This has 4. So this is the one that has the fewest. 3 digits to the right of decimal. Our answer should also have 3 digits to the right of decimal. So we should round this off to make sure that we have 3 digits to the right of decimal. And we do that. So we should round this digit off by looking at this digit. It's above 5. So we round up. So 804 milliseconds. Notice that I didn't really care about what units we are dealing in. None of that matters. As long as you're adding and subtracting, this is the rule. The whole idea is when you're adding or subtracting, you first find which measurement has the fewest digits to the right of the decimal, and then make sure that your final answer is also rounded to match the same number of digits, fewest digits to the right of decimal.